Okay, let me get you to think about circuits a little bit and light bulbs and power that's associated with that. So let's look at a circuit here. So I've got one that's shown here. I've got a 5-volt battery and I've got a series of resistors and switches, right? So I've got a 10 ohm resistor here, 20, 10, another 10 ohm, and 15. I've got two switches here. Couple of points to make about switches. So notice this is open, so nothing is happening. If I was to close this switch, I would short out this circuit, right? So I could have my electrons flowing from my positive side to my negative side, and the charge would flow along the path of least resistance, and it would bypass all the resistors, right? So if I close this switch, none of the current actually flows through any of the resistors. So not so interesting. If I close this switch while leaving this other one open, then I'm going to change my circuit now, essentially cut off this resistor, so my system will change. So you have to be careful about switches. So I'm going to assume the switches are open for this one, and let's work through how to analyze this. What I'm curious to know is, well, what's the current at all of these resistors? Right? Well, my favorite way to go about this is to label these. So I'm going to give these numbers that I'm going to follow through. So I'm going to call this resistor 1, I'm going to call this 2, call this 3, and call this 4. And what I'm going to do is I'm going to make a table. I'm going to call this an Erv table, right? So my Erv table, I'm going to figure out what is the current, what is the resistance, and what is the voltage drop across each of these resistors, 1, 2, 3, 4, and then I also figured out across my whole system, across my total system. So let's fill in the things that we know, right? So what do we know so far? So we know the battery is providing 5 volts. So my total voltage here is going to be 5 volts. What else do I know? Resistor 1 has 10 ohms of resistance. Resistor 2 has 20 ohms of resistance. 3 has 10 ohms. And 4 has 15 ohms of resistance. So what I'm going to do is I'm going to try to work my way to fill in everything on this table, and then I'll be able to know the current that's passing through any of these points, including the total current that's leaving the battery and arriving back at the battery. So my way to do this is, well, I'm going to simplify my circuit. So here I have 3 resistors that are in series. So I'm going to replace those resistors in series. I can just add together the resistance of those. And so I can replace those 3 resistors with one that has, 20 ohms plus 10 ohms plus 15 ohms. I'm thinking this is 45 ohms of resistance. So I could draw a new circuit, which is going to have my 10 ohm resistor here. And I could have one that had, instead of those 3, now has one that's 45 ohms. Well, now I can figure out, if I wanted to, figure out a couple things. So one, I could use a loop rule here. I could use a loop rule to say, well, what is the voltage drop across any of these 2 resistors, right? And my loop here, my voltage gain must equal my voltage loss. So I have a 5-volt battery that's just generating 5 volts. I must be losing 5 volts across this resistor. So I know resistor 1 is going to have a voltage drop of 5 volts. Now this one I just made up, so I don't know, but the total voltage drop across all 3 of these needs to be 5 volts, and we can check that and see if that works out. But not quite there yet. I can go one step further and I can figure out what is my total resistance for my whole circuit. Now I have 2 resistors that are parallel, resistors in parallel. Right, to calculate the resistance, I'm going to take 1 over my total resistance is going to be 1 over resistor 1 plus 1 over resistor 2. Right? And when I do this, I'm going to have, what am I going to have? I'm going to have 1 over 10 plus 1 over 45, and that's going to be careful. I'm going to be careful. That's 1 over my total resistance. And so what am I going to get? I'm going to get 5.5 over 45. It's 1 over my total resistance, so I'll flip both sides of this, and it's going to be, what, 8.2? So my total resistance for things that are in parallel is going to be 8.2 horseshoes. So I know now my total resistance is 8.2 horseshoes, and now I can start erving this, right? So remember, current times resistance is going to equal voltage. This is Ohm's law. We're assuming everything behaves ohmic, which means I can use this law. So I can figure out now that my voltage is 5, my resistance is 8.2. This is going to leave me with a current of 0.61 amps. So what that means is that at this point, I'm going to have 0.61 amps leaving this battery and 0.61 amps arriving back at the battery here. Remember, my current is going to get split. Remember my junction rule, so I'll have current going in here, so whatever current I have going in must equal the current I have going out, but I don't know, right? I don't know how to split this yet. Right? But let me work my way through a table. So now I'm doing circuit Sudoku. So I have current and I have resistance and voltage here, so I can figure out current. So I'm going to have 5 divided by 10, so it's going to be 0.5 amps of current. Well, that's interesting. So I know that coming into here, I have 0.61 amps. And coming down this path of it, I have 0.5 amps. So I can figure out this one must be the difference of those, so 0.11 amps. So I know going into resistor 2, I have 0.11 amps of current. And I have a line here, so this is just like a pipe of water, so whatever water goes in here must come out the other side. So the current through all of these is going to be the same, 0.11 amps. And now I can math it, so I can come up with 2.2 volts here, 1.1 volts here, and 1.7 volts here. I could check, so these three should add together to give me 5 volts. Right? And you can check it, but I'm pretty sure that works out that way. Okay, so this is one way to get through a simple circuit. So let's make it a little bit more complex. So let's, instead of resistors, let's pretend that we have light bulbs. And all light bulbs are resistors that are in glass. So I'm going to draw a glass. I'm going to pretend each of these is a light bulb now. There we go. I've changed my circuit diagram. I don't have resistors anymore. I have light bulbs. And the question is, well, which one is the brightest? Well, this is a fun question, because the brightness, right, is not necessarily related to current or resistance or voltage. Brightness, remember, light is a form of energy. So brightness is how much energy per second is being reduced, right? So produced. So I want to know energy per second, and you may recall this from back in mechanics, right? This is power, and I'm going to measure that in watts. Right, so this is my light bulb. So we used to measure light bulbs by how much power they consumed, right, rather than how much light they put out, which we use lumens now, which is a better measure because it measures the light that's produced. Because LEDs don't take as much power to make the light. But anyway, we have a measure of power. So in a circuit, though, I'm going to have a measure for power, which I can calculate as current times the voltage. So for any of my light bulbs here, if I know the current and the voltage drop, right, then I can multiply those two together, and that'll tell me the power. Right? And hopefully this makes sense to you, right? So current is the flow of electrons. So how many electrons, or how much charge is flowing through here? So that's the rate of the flow of charge. And voltage drop is, well, you know, how hard is that being pushed? Right? So, you know, how high is the dam, if you like? So the voltage drop is, if I have a lot of current is being pushed really hard, right, I'm generating a lot of power there. I'm using a lot of power. Resistors by themselves, they generate heat, right? So every resistor is going to be losing some energy, right, as the electrons smash through there, as my charge smashes through a resistor. The special thing about light bulbs is that heat is heating up a filament, and that filament is glowing, so that some of that energy is being transmitted in the form of light. So, but all resistors are going to be generating power. Usually that the power is going to be in the form of heat. Okay, notice that I have I and V. Well, I can use Ohm's law. So I have 3 different ways I need to calculate power. So I could put it as current times voltage. I could have current squared times resistance, and I could have voltage squared over resistance. So these are all 3 different valid forms, depending on what I have. In this case, I've done all sorts of calculations. So if I want to figure out which one is the brightest, or which one, the question is how much power is being produced. And for this, I'm just going to use IV, so I'm going to multiply current times voltage. And when I do that, in my table, I'm going to have 0.25 watts of power being produced in this first resistor light bulb. I'm going to have 0.24 watts of power produced at the second one, 0.12 watts, and what's the last one? I got 0.19 watts of power. right? So this is energy that's being dissipated in my circuit. And if I was interested in which one is the brightest, that's going to be the one that produces, that has the largest amount of power. And power is the energy use per second. So I hope that's helpful. So what we've taken a circuit, we've looked at resistors, we used an Erv table. I've added a P in there. I'll call this an Erv-P table. So if I needed to get to the power or brightness of light bulbs, for instance, I would use a table that looks like this. These tables are really helpful for sorting through, right? We're just using Erv over and over again in different ways. We're dealing with resistors, and pretty soon we're going to throw capacitors in here just for fun. Hope that's helpful. Talk to you soon. Bye.